I ended last lesson explaining what we're going to be doing in this video here, but we're still using our law of uninhibited growth or decay. But now I have to come up with my own formula. So example 3 says a culture of bacteria obeys the law of uninhibited growth. And I get this straight from my math lab. So in my math lab, it's going to ask you if N is the number of bacteria in the culture and T is the time in hours, express N as a function of T. When you come to that problem in my math lab, literally all they are wanting you to do is write this formula, but instead of A, they want whatever variable they tell you, and they tell you in this one N. So instead of A of T, it is now N of T. Instead of A naught, it's N naught, and then the rest will be the same. Okay, so that's all you're doing. I think it's kind of silly, don't know what the point is really, but that's what happens. Okay, so part A, check, done. So now, part B says if 300 bacteria are present initially, so that means this right here is my N naught. And there are 475 after 1 hour. So this is my N of T. And my T, how many will be present in the culture after 5 hours? So let me get a highlighter here. I am using this first half of this sentence right here to build my formula. So you can see here, we have an N naught, our N of T, and our T. What I'm missing here is my K. I don't have my rate. So let's plug in these three, and then we're going to solve this for K. So I have 475 equals 300 e to the K times 1. So let's figure out K here. So same thing, whatever this initial amount divided over. Now, I've been saying this in examples 1 and 2, and here's what I'm talking about. When I divide this, I don't get a decimal that stops. I don't get a nice 0.7 or a nice 0.5. I get a decimal that keeps going. So I cannot convert this one to a decimal. I need to keep this as a fraction. Do not round until the very end. If you round on step 1, and then you round on step 2, and then you round in your final answer, every time you are rounding, you are getting further and further from your answer, from your exact value. So do not round until the end. I am not going to call that 1.5 or 1.6 or 1.58 or 1.583. I need to keep this exact. So we're going to call this 19/12. Do not round until the very end. So we have 19/12 equals E. K times 1 is just K. And now rewrite it. So we have base at the other side of the equals, means I have the natural log of 19/12, and that's going to equal my exponent of K. Now we can put this in our calculator and get a decimal answer, and in my math lab you might need to. So K is going to be about about 4.5, we'll call it 9.5. But I am going to use my exact until the very end. So I will be using this as my K. You need to read the instructions in my math lab. It might ask for what K is about and then wants you to use your rounded version. I'm not sure, but good practice is to use your exact until the very, very end. So now I'm just going to go ahead real quick and rewrite this formula here. and I'm going to plug in my values. N of t is something that we would be finding. My initial amount isn't going to change. So this is 300. E, I know my K. And then that is to the T power. This right here is me building my formula. Okay, when you're building your formula, you should know your initial amount and you should know your K. What we won't know is our N of t or our A of t or P of t, whatever this equals, and then the time. So this is my formula. So now we can answer the rest of this question. Now that I've had my formula built based on this first half of this sentence, it wants to know how many will be present in the culture after 5 hours. So now I will take this formula here and I'm going to find N of 5. So N of 5 equals 300 E to the natural log of 19 over 12 times 5. And so we will have about, and again, make sure you are typing these in, because the further we get into here, the more complex these are going to be getting. So we're going to have roughly, let's just round to the nearest whole number, 2,985 bacteria. Okay, we're going to go over examples 4 and 5 that are going to be very similar, where I have information that I'm going to have to build my formula from, and then I can answer the actual question it gives me. So, example 4. Says a population of a southern city is growing according to the law of exponential law. So remember, that's the same thing as uninhabited growth or decay. So if P is the population of a city and T is in, so if P is your population and T is in time and years, express, a little bit of a typo, let's express P as a function of T. So again, all that this is asking us is to write this formula, but instead of A, we're doing P. So this is P of T equals P naught E to the KT power. You're going to get a question like that in my math lab. So now, if the population doubled in size over an 18-month period and the current population is 10,000, what will the population be in 2 years? I am actually building my equation over this first part right here. If the population doubled in size over an 18-month period. Okay. So from this formula here, I don't know what my P of T is. And I actually don't even know what my initial size of my population is. So let me just go ahead and write this formula here so we can see what we're substituting into what real quick. Okay, I don't know my P naught. I don't know my initial size. All I know is that it is doubling. So play with me here. If my initial population was 10, if it doubled, then my P of T would be 2 times that 10, it would be 20. If my initial population was 50, then my P of T would be 100. If my initial population was 250, then this would be 500. Whatever this initial amount is, this is going to be 2 times that initial amount. So when it says it's going to double in size, we're going to put our P of T is 2 times that initial amount. And then we have E to the K. I don't know K, but I know that my time is 18 months. Now there's a slight problem with that. And what is my problem with 18-month period? Well, we've underlined up here what my time stands for, and my time is in years. And they're giving to me my time in months. So we need to convert that. And there are 12 months in a year. So we'll do 18 divided by 12. So from here, I would still, to solve for K, I would still want to isolate this exponential portion here. So to do that, we would divide our initial amount over. We have P naught cancels with P naught, and they also cancel over here on the left. So we are left with 2 equals E. 18 over 12 is 1.5 times K will give me a 1.5 K, which should make sense because we have shown that if we're doubling, once we divide that initial amount over, this should equal 2. So now rewrite this. Base to the other side of the equals will give me a natural log of 2. And that's going to equal the exponent of 1.5K. And then to get K by itself, divide that 1.5 over. So K is going to equal the natural log of 2 over 1.5. Okay, so now I have my K. So now let's build a formula. The current population is 10,000. So this is going to be my P naught. What will the population be in 2 years? So we'll get to that 2 years part here in a second. Let's just build our formula. So if I rewrite this again, we have found the P naught is 10,000. And we have E, my K, is the natural log of 2 over 1.5. And again, if they ask for a decimal equivalent of K, you might be using the rounded version here. So just read what it asks. And then I don't know my time. So time is T. So this is me building my formula. When you have your formula, you know your initial amount and you know your K. We won't know our P of T, A of T, N of T, and we won't know T. So now we can find out what the population will be in 2 years. So we'll take this formula and we'll find our P of 2. So we get 10,000 E to the natural log of 2 over 1.5 times 2. And so P of T is about what? And again, make sure you can put these in as these are getting more complicated. And so we get about 25,198. We're rounding to the nearest whole number because we're talking about people here. That is what my population will be. Okay, one more example, and there's not any parts to this. It's just, here's the information, answer the question. A piece of charcoal is found to contain 30% of carbon-14 that it originally had. When did the tree die from which it came? Use 5,730 years as the half-life of carbon-14. So because we're talking about half-life, I do know I'm going to have a decay rate. And I am going to find that rate and build my formula based on that information only. Okay, so doesn't tell me what variable to use, doesn't matter which. I'm just going to use A of t like we have in our formula. So we have A of t equals A naught e to the kt. I am only told that I have a half-life here. So just kind of like doubling, we had P naught and now 2 times my P naught. My half-life means whatever my initial amount is, I will then have half of this over here. So if A naught's 100, now it's 50. If A naught is 700, now this is going to equal 350. Whatever the initial amount is, I'm going to be left with half of it over here because we were told half-life. Then E, I don't know my rate, but I know my time is 500 or 5,730 years. So solve. Just like before, I need to divide this initial amount over, and when I divide this side by A naught, this side will also lose its A naught. So I have 1/2 equals E. When I multiply these together, we're going to get 5730K. Rewrite this. Base to the other side of the equals will give me the natural log. I'm going to put this as a decimal. But you can keep that as 1/2 if you want. Equals 5730K. And then divide that K or that number over to get K by itself. So K equals the natural log of 0.5 divided by 5730. Okay, so let's build a formula now. So I'm going to take this here and we're going to have A of t equals my A naught. If this piece of charcoal that I found contains 30%, then how much of that percentage did it originally have? It's going to come from 100%. Contains 30% of what it had. So my A naught is 100. E to the K, the natural log of 0.5 over 5730 T. So here is my formula. So if a piece of charcoal found contained 30%, this is my A naught that it originally had, and we said originally it had 100%. Then it wants to know, when did the tree die from whence the charcoal came? I need to solve for T. So I've got to go through this process of solving again. So we have 30 equals 100 E to my KT. So to solve for T, we need to divide this original amount over. 30 divided by 100 gives me 0.3. That's a good decimal. I have that exponential isolated, so let's rewrite it. When I go base to the other side of the equals, we get natural log of 0.3. And that's going to equal this right here. And the last step to get T by itself is to divide that entire thing over. So we have T equals, in the numerator, I have the natural log of 0.3. And then in the denominator, I have a fraction here of the natural log of 0.5 over 5730. And so that's going to give me about what? So I'm going to use my N over D here. We have natural log of 0.3 divided by, just put in another one, because why not, in the denominator, we have the natural log of 0.5 divided by 5730. So if we round to the nearest year, we're going to get 9,952 years. So, super old piece of charcoal. It has seen some things. Okay, that's the end of uninhabited growth and decay. When we go on to the next video, we will start using logistic models.